Hey everybody, as we've been going through this chapter on transforming graphs, we've gone back and forth from equations to graphs and graphs to equations, and here we are back at equations, and can we make the graphs? These are called a whole bunch of different words as you look at different math textbooks. Sometimes these are called stretch, or sometimes it's called stretch factor. Sometimes it's called a coefficient. Sometimes it is called a dilation. What else did you learn maybe in geometry? Stretch, coefficient, dilation, zoom factor, sometimes you've heard in previous classes. I like to call it the stretch. The thing that you don't want to call it, I'll write it here and then I will cross it out, is you do not want to call it slope. Excuse me. A few of these graphs are straight lines, like the absolute value over here. But other than that, we have curved graphs. So we don't want to be using slope. Slope is a constant rate of change. It's linear, and most of these are not linear. So I will go ahead and reference it today as the stretch. That's what I'll use on the test. But you can talk about these graphs doing lots of different things. So on our red graph, what we can always do if we get in trouble here is we can make a table, we can plug in numbers, and we can see what happens. Our goal this chapter is maybe to do it, the most efficient way. So if you think about plugging in 0 squared is 0, 0 times that 3 out front doesn't do anything. We still have 0, 0, right? When you plug in 1 squared is 1, times 3 is 3. Cool, and the same thing's going to happen when you go to -1. -1 squared will be 1. 1 times 3 is 3. Just take a look at the shape of the graph right here. At this moment, it could be a V shape, absolute value. It could be a quadratic. It could be a parabola. We look at the x squared and we know that it's going to be our quadratic, our U-shaped parabola. Look at what the graph did. It still has the U shape. It just stretched 3 times taller. It kind of worked like slope. When you went over one spot, it went up 3. But I want you to think for a second. When I go to the next point on this graph, is it going to go over 1 and then up 3? Well, that's called slope. And remember, I crossed out slope up top here. It is not slope. It is not going to work like that. It only works for that first spot. So when I go one spot over, I can do this stretch of 3. But watch what happens when you go 2 spots over. Plug in 2. 2 squared is 4. 4 times 3 is 12. When I go over to my second point and I go up 12 way off the graph here, we can see that that is not a linear graph. It is not slope. So I don't need to do that today. I just wanted to show you that just because you go 3 for the first point doesn't mean that you go 3 for the next point. It is not slope. Okay? So all we're looking for today is a couple of key points. We got 3 key points. And we got the shape of the graph as our quadratic parabola. Cool, let's go to the blue graph. We know that the square root starts at 0, 0 in the middle. You can plug it in. The square root of 0 is 0. 0 times 3 is 0. And then you can plug in the next point. What is the square root of 1? 1. 1 times 3 is 3. Just notice that kind of like this last graph, we started at 0, 0, and the next point was stretching 3. We have the same thing here. But that could be a line, it could be a quadratic, it could be a parabola, it could be a million things right now. But we know that the shape of the square root graph curves like that. I don't want to go over another 1 and then up 3. It is not a line, it is not slope. We do not want to be using slope. This is called a stretch, it's called a coefficient, it's called a zoom, it's called a dilation. It is not called a slope, okay? But we're kind of treating it like slope just for that one point, okay? Take a look on this one. Our stretch is a -3. Well, we know what the absolute value looks like. It starts at 0 and it's that V-shaped graph. Again, you can always plug in a number. What happens when you plug in 0? The absolute value of 0 is 0. 3 times 0 is 0, that's why we have that point. Plug in 1, what's the absolute value of 1? That's 1. 1 times 3 is 3. Oh, but it's a negative out front. It's a negative out front. So our stretch of our graph is going to stretch over one spot, and then down 1, 2, 3. We know what the absolute value looks like. It's a V shape, it's symmetrical, so I can go ahead and put another point on the other side. This one I can draw a straight line, so I actually could use the word slope on this one, but I like to use things that work for everything, so I'm not going to use slope because slope only works for this linear one here for the absolute value. It doesn't work for our other graphs. Notice how it's stretching down 3 on both sides. We'll go back to the red graph. Notice how it's stretching up 3 on both sides. Take a look at our square root graph. Notice how it's stretching 3 on, it's not stretching 3 over here. Why not? You can't take square roots of negatives, so you got to know those shapes of the graph. Last slide. Some of them are going to be symmetrical on both sides, right? The green graph and the red graph are symmetrical on both sides. All right, we'll go ahead and take a look at our next one, and we're going to change the stretch on each of these graphs. This first one is our hyperbola. That's the tricky one, but we're stretching it 4 spots. So go over 1, stretch it up 1, 2, 3, 4. And then we know that we draw our hyperbola and it gets close to the x-axis as it comes down. We don't have to be perfect this chapter. I'm just looking for you to plot a couple key points. We know that our other part of the hyperbola happens down here. So what do you think? Excuse me. What do you think? When I stretch a spot over to the left, I'm going to have to go down 1, down 2, down 3, down 4 to plot that key point for my hyperbola to go through. So I've got to know the shapes of the graph in order to do these stretches. Some of these are not symmetrical. The hyperbola is positive on the right and negative on the left. So we just got to know the shape of the graph, get those key points. Cool, let's go to purple here. Notice that we have a negative and we have a decimal. That's totally okay. We know that x squared starts right in the middle. When we go over one spot, it's going to stretch down a half a block. And then what's the shape of a parabola? A quadratic, it's symmetrical. So whatever I do on the left, I better do on the right. So when I go over a spot on the left, I'm going to go over here. Remember, this is not linear. I do not want to be making a line through these. That's the absolute value, or that's linear. I do not want to be doing that. So I just plot the key points, and then I know the shape of the graph is a U-shaped graph. So I just draw that U-shaped graph in there. Cool, and then we'll finish off with the red one. We got absolute value again. We got a negative. We have a fraction. What I want you to keep in mind for this one, we know that absolute value starts at 0. We know what a V-shaped graph looks like. If this is negative, we know it's going to be upside down. I do not want you to treat this like slope. Do not treat it like slope, okay? Don't. It does not mean go down 1 over 4. What your stretch factor is when you go over one spot on the graph, how much does it go? Is going down 1/4 or down 1/4. I am simply just down a quarter of a block, and it's a symmetrical graph. I'm down a quarter of a block, then I draw the shape of my graph, okay? Do not treat it like slope, even if it's linear. I know the absolute value is linear, but on any of these problems, especially the fraction ones, don't treat them like slope. Your stretch factor only works when you go over one spot. So go over one spot and then plot that point or plot that stretch.